Encryption provides confidentiality, but we also need integrity. For a system to be secure, we need to know that a message was actually generated by someone else and no one has modified it. So, for example, suppose we want a secure file system protocol. Without integrity, an adversary could append garbage data to writes or potentially create new write commands with garbage data. The basic point is that secrecy is not enough. Encryption can prevent someone from reading our messages, but it doesn't protect them from tampering. The second property of secure systems, besides confidentiality, is integrity. Integrity algorithms let you know for sure that a message was generated by someone with a key. So assuming the key is secret, then you can be assured it came from a specific program, host, etc. This is really useful. For example, with integrity, you can know that a routing vector actually came from the node it supposedly came from. An adversary isn't trying to trick you into routing traffic through them. You can know that the person who's making a bid in an auction actually made that bid. And you can know if you receive a message to terminate a connection or a bad message that might cause you to terminate the connection, that the message actually came from the other endpoint and isn't someone trying to shut down the connection on you. Generally speaking, in security, integrity usually comes first. There are lots of cases where you want integrity, but confidentiality isn't that important. But it's very rare that you want confidentiality without integrity. Cryptographic hashes and message authentication codes are two major integrity primitives. Cryptographic hashes let you safely determine the data hasn't been modified. Anyone can generate a cryptographic hash. They require no key. It's a hash function with some special properties. Cryptographic hashes are useful for storing data. You can be sure no one has tampered with the data, and since no key is needed, anyone can check that the data hasn't been tampered with. Message authentication codes, or MACs, are a second way to verify that data hasn't been modified. They have all of the integrity properties that cryptographic hashes do, but they have the additional property that they ensure that the person who generated the MAC has a key. So only someone else with the same key can check that the MAC is correct. So message authentication codes are useful in networks. If you send a message with a MAC appended to it, the receiver, if they have the corresponding key, can check that the message they receive is the message you sent, that you sent it, and since you had to have had the key to generate the MAC. In that way, MACs also provide authentication, hence their name. So let's look at cryptographic hashes first. A cryptographic hash is a hash function with some special properties. Like an ordinary hash function, a cryptographic hash produces a fixed length output from an arbitrary length input. For example, I can compute a 256-bit hash from a gigabyte of data. They're generally very fast to compute, faster than the network. Cryptographic hashes, like normal hash functions, typically work by performing a single scan over the data and performing some mathematical operations based on each byte or word. That way you don't have to keep the entire data in memory at once, you can just stream through it. Cryptographic hashes provide the property that they are collision resistant. What this means is that if I have some data x and a hash h of x, then it's intractable to generate a message y such that the hash of y is equal to the hash of x. Of course, there are many such collisions. So let's say I have a 256-bit cryptographic hash. There are 2 to the 256 different values this hash could take. Let's say I'm hashing a gigabyte of data. Well, there are 2 to the 30 bits, so 2 to the 30 different blocks of data, but only 2 to the 256 different hashes. So while such collisions exist, they are very difficult to find, such that people spend years trying to do so and don't. You can't just try 2 to the 120 different data blocks. This is a very, very deep idea. Make sure you understand it. Given a hash value h, it is intractable to generate a piece of data that has that hash value. This might seem very simple, but it is amazingly powerful. Given a hash value h, it is intractable to generate a piece of data that has that hash value. If you need to use a hash function, then use SHA-256 or SHA-512. These are the SHA Secure Hash Algorithm 2, SHA-2 algorithms with either 256 or 512-bit hashes. SHA-1 is nearly broken today. There's also SHA-3, which the National Institute of Standards and Technology selected in October 2012 to be an alternative hash to SHA-2, which is just as strong, but based on different mathematical principles. That way, if there's something wrong with SHA-2, we can fall back on SHA-3. Now, SHA-2 was designed by the National Security Agency, or NSA, and published in 2001. Given all the recent press on the NSA trying to build backdoors, you might think there's one in SHA-2. Really, chances are there isn't. It's been around for over a decade, and it was vetted in a public process. Anyone who's anyone in cryptography and security has taken a look, and it seems fine. Breaking SHA-2 would be the equivalent of developing Einstein's theory of relativity in physics. SHA-3 was designed by a group of security researchers and won a competition sponsored by NIST for the new SHA-3. Cryptographic hashes have this nice property that a small hash uniquely describes a very large piece of data. The basic approach is this. Take your file and compute its hash, store this as h1. Later, compute the hash in the file again. Let's call this hash value h2. If the new value doesn't match the old one, then something has changed in the file. If the two are equal, then you know the file hasn't been tampered with because nobody could generate a new file or change the existing file so that it has the same hash value. So something you sometimes see when you download software is someone publishes the hash of the software alongside the program. You can then check that what you've downloaded is what they produced, so nobody's inserted malware into the distribution after it was released. One neat way you can use hashes is something called a Merkle hash tree. So by themselves, cryptographic hashes just tell you if the data has been modified. If I have a huge file, I can tell it's been modified, but not where. If you build a Merkle hash tree, you can tell which part of the file has been modified. You hash small blocks of the file, then create a tree of hashes like shown here. If the top level hash differs, then you know the two files differ. You can then walk down the trees and in a logarithmic number of steps, figure out which part of the files differ. So if someone has tampered with your file, you can see if it's because someone truncated it by accident or if they inserted malicious code. So cryptographic hashes are very useful, and they tell you if nobody has modified the data, but they don't require a secret. Anyone can generate a cryptographic hash. Anyone can check a cryptographic hash. Message authentication codes, though, want to provide authenticity as well. You want to be sure that the program that generated the MAC has a secret. So building message authentication codes is easy once we have cryptographic hashes. All we need to do is incorporate the secret into the hash. We can define a message authentication code algorithm, HMAC, which takes a key K and a message M. All it does is prepend the key to the message and compute a hash over that data. You can then send just the message and the MAC. To check the message authentication code, the receiver prepends the key, computes the MAC. They know only someone with the key could have produced the MAC. So it's simple. We have a cryptographically strong MAC. Wrong. Recall that hash functions work by iterating over the data. So for most hash functions, this means you incorporate the new data into the existing hash value. Put another way, the hash value is the intermediate state of the computation. This means that if I see a message M that has a certain MAC, I can append some data to M, making M prime, and compute the MAC for M prime. So, as it always seems with security, the simple approach doesn't work and has vulnerabilities. We need to do something smarter. Luckily, that smarter approach is not much more complex. Here's the right way to compute a message authentication code. Take your key K and XOR it with an inner pad, let's say 0x36 repeated 64 times. Take a hash of this inner key K prepended to the message. Then, compute an outer key by XORing K with a different outer pad, say 0x5c repeated 64 times. Hash this outer key and the result of the inner hash. So why doesn't the previous attack work? Well, suppose your attacker appends some information to M. They don't know K. The MAC, however, is made up of the hash of M, not M itself. So appending to M will result in a completely different hash value. The intermediate state of the computation leaked in the previous approach is hidden through this inner hash. So this is how MACs are generally computed today. You take a cryptographic hash of a transformation of the key and the message, and a cryptographic hash of a different transformation of the key and that hash. So, one final problem. Let's say you have both confidentiality and integrity. Should you encrypt the MAC or MAC the encrypted data? The answer is the latter. MAC the encrypted data. There are some cases where encrypting the MAC is not always secure, so always MAC encrypted data.